All right, so now we have our second problem set involving optimization. This one's going to be about volume. So again, we are going to be looking for maximums and minimums. So we're going to write a function for the situation, and then we're going to ask when that function is equal to 0. So in this case, we're going to be looking at, as I said, volume. So there's going to be some formulas, like if you don't remember the volume of a sphere, that's fine. Feel free to look up anything that you need to in terms of formulas. If you're stuck on any, and this is a reiteration of the email that I sent out earlier, please ask for help. I am here. I want to give you time to work through these things. I'm very relaxed about deadlines because I want to give you time to work through these problems. But if you don't reach out for help, that time is not going to be as efficiently used, and you're going to spend a lot more time being frustrated versus finding 10-20 minutes in your day to talk with me, and we can get you all the way caught up and feeling a lot more confident about the content. So let's look at a volume problem. Here, a cylindrical can must hold 1 liter of water. Find the dimensions that minimize the cost of the can. Now here is a little bit of logic that you're going to have to go through. Okay, well, it is a optimization problem because we're asked to find the minimum of a cost. Now, minimum of a cost of the can, you're going to have to use a little bit of logic and leap here, because what this means here is that you're trying to find the minimum of material, and this will come up in some of your other problems, so hopefully explaining this thought process will help. Minimum of material used. Now, the material used to make the can is the surface area. So this is the function that you actually want to use, is you're looking for where the surface area's derivative is equal to 0. Now, let's review cylinders. As I said, you can look up formulas as you need them. So we have the cylinder, and the surface area is equal to 2 pi r squared, which is the area of the top up here, and then the bottom has the same area, plus the area of the sides all the way around. Now, if you unroll that, it forms a rectangle with the circle on the top and the bottom. And the height of that rectangle here is the height of the cylinder, and the length here is the circumference of this circle, so that it wraps all the way around the can. The circumference is 2 pi r, and then the height like so. So that's the surface area function that you're going to be taking the derivative of, because you want to find the minimum of the surface area. So surface area is equal to 2 pi r squared plus 2 pi rh. Now, just like before, we want to reduce those variables. So we want to find, we've got r and h. We have r twice, so we probably want to replace h. Makes sense. So that's where you're going to use your other stipulation here. We see that it has to hold 1 liter of water. So we know that volume is equal to 1 liter. Now we're measuring things in radius and height. We are measuring things in terms of length. So you're going to want to remember from your chemistry classes that this is equal to 1,000 centimeters cubed, because centimeters is a unit that I can actually measure radius and height in, versus liters, I can't measure radius and height in liters. So we want to convert that into a unit that makes sense for the problem. And then we'll remember that our volume of our cylinder is pi r squared for the base times height. So pi r squared h. We want to replace h, get rid of it, so that we have fewer variables. So divide by pi r squared. So it's 1,000 over pi r squared is our height, giving us the function surface area is equal to 2 pi r squared plus 2 pi r times 1,000 over pi r squared. Do a little simplifying before I take the derivative because it's just easier. Cancel out pi, cancel out r. We end up with 2 pi r squared plus 2,000 from the 2 times the 1,000 here over r in the denominator. That I'm going to write as r to the negative first because it's just easier to differentiate like that. And now since we are left with just r as our variable, I will take the derivative in terms of r. So surface area prime is equal to 2 pi r squared, so 2 pi times 2r for the derivative, plus 2,000 times negative 1r to the negative 2. So just using the power rule for the two different terms. Now what I want to do is simplify this down. And I will then say 0, since that's, I want to find the minimum, of 4 pi r minus 2,000 r to the negative 2. I'm going to write this now as a fraction and add it over, so that I have positive 2,000 over r squared is equal to pi r squared. Oh, not just squared. So I added this and then wrote this as a denominator. Then I'm going to multiply by r squared up. So then I get 2,000 equals 4 pi r cubed. 2,000 over 4 pi is equal to r cubed. Get that by itself. Cube root. Since this doesn't cube root nicely, that's absolutely fine. If you want to simplify 2,000 over pi to 500 over pi before you take the cube root, you can. But you can also just plug that into your calculator. If you don't have a cube root button, which most of you don't, remember that this is a power of 1/3. So in terms of my calculator, I'll type in 2,000 over 4. Use the pi button, don't round, to the power of 1/3, which gives us our radius, which is 11.624. And it asks for both of the dimensions. So what that means is that you're also going to want to include the height. Now remember from our function here that height is equal to 1,000 over pi r squared. So I'm just going to use my calculator, use the answer key to plug in r squared, since we just learned that r is 11.624 centimeters. Type that in, 1,000 over parentheses pi, and then answer squared, and I get that the height is equal to 2.356 centimeters. Again, if you have questions or are stuck on anything, please reach out. Don't feel like you have to struggle through them on your own. I am absolutely here to help, and I look forward to hearing